So, let us now make it mathematical. How do we do that? Let us again go back to fluid flow. And I will make in this a rectangular small box at some point x, y, z with x axis this way, y axis this way, z axis this way, and this is point x, y, z. Let the size of the box be a in the x direction, b in the y direction, and c in the z direction. Let me make this box separately once more. This is the box with this side being A, this side being B, and this side being C. Let us calculate, because now water coming in and water going out looks like there is more coming in than going out. Let us really see what happens. Let us look at the surface. Let me name it 1, 2, 3, 4, 5, on the back side 6, 7, and 8. Let us look at the point 5 is my x, y, z. Let us look at surface 5, 6, 7, 8. Five, 6, 7, 8 is perpendicular to the x axis, and if there is a velocity of fluid v, we are talking about velocity field. If there is a velocity v, then fluid passing through 5, 6, 7, 8 per second will be really, if you make a big rectangle of length Vx, whatever the fluid is in this Vx is going to pass through the surface, right, because in 1 second it will cover the length Vx. So, fluid passing through this is going to be Vx times the area is going to be B times C. This is a fluid passing through it. Let us make it more precise. This is the box. And I am interested in what fluid is going out, right. So, for that I need the component which indicates a flow out, and that is for 5, 6, 7, 8, the component in minus, this is my x axis, in minus x direction is going to tell me whether fluid is leaving or coming in. So, fluid leaving, magnitude we already said is Vx Bc, which is Vx at x and y and z Bc, and which component? The component in the minus x direction. So, I am going to write this as V dot x in the minus direction at x, y, z, Bc. This is fluid leaving from 5, 6, 7, 8. Let us look at surface 1, 2, 3, 4. At 1, 2, 3, 4, fluid leaving would have that component in the x direction, and therefore, fluid leaving the volume, the box through 1, 2, 3, 4 is going to be equal to the component of V in the x direction, right, coming out of the volume, right, times B c again, and this V though is going to be at x is now x plus a. Remember, the surface 5, 6, 7, 8 is at x. This is going to be x plus a, but all other points they have the same, all the points have same y and z, B c, right. So, which I can write as V x at x plus a, y and z, B c, which I can further write as V x x y z B c plus partial derivative of V x with respect to x B c, with the result that net flow through surfaces perpendicular to the x axis is going to be minus V x at x y z B c plus V x at x y z B c plus partial of V x by partial x a, b and c. This is the change in V x through a. Let me see if I wrote that a earlier. No, I did not. So, there should be an a here. This cancels and we are left with partial V x by partial x a, b, c. In a similar manner, similarly, you can show that net flow through surfaces perpendicular to the y axis is going to be partial V y over partial y a b c, and net flow through surfaces perpendicular to the z axis is going to be partial V z over partial z a b c. So, overall through this box, if I count all the surfaces, the net flow is a b c is common, partial V x by partial x plus partial V y by partial y plus partial V z by partial z. We have of course assumed that a, b, c are small. So, I kept only the first order, and which is nothing but small volume of this box times what I said earlier. I am going to write it as divergence of V, where symbolically this symbol is going to be x unit vector partial x plus y unit vector partial y plus z unit vector partial z. So, that when I write divergence of V, it is partial x plus y partial y plus z partial z dotted with, and I am going to take the dot product first, x V x plus y V y plus z V z. If I take the dot product, x dot x gives me 1. So, I am left with this plus y dot y gives me again 1 d v y by d y plus partial V z by partial z. All other dot products give me 0. So, what we have found is that if I take a small box of very small volume and talk about this fluid flow through this, then the net flow, which now I am going to write as V dot x, and we had written, remember, B c plus V at x plus a y z dot x b c, and other components is actually nothing but V dot d small area, where the direction of area is equal to pointing out of the volume. So, what the quantity we have calculated is this. We have actually calculated this quantity, which is nothing but V dot ds integrated over the entire area. All right, and what we have found is that V dot this small area ds is nothing but equal to divergence of V times the small volume delta V. All right, let us rewrite it. If I rewrite it, I have this box, very small box, and if I calculate V dot ds, let me write it even better, sum over all the surfaces, surface 1, surface 2, surface 3, surface 4, this is nothing but equal to divergence of V dot d volume, and this defines divergence consistent with the ideas I was talking about earlier. If there is a net flow outside, if there is a net flow through the surfaces, notice that this is a positive quantity. So, divergence of V is not 0. If there is no net flow, divergence of, if there is no net flow, divergence of V is 0. As I said earlier, if I take a point source of light, right, all the rays are diverging from it, because there is a net flow of light from here. Similarly, if there is a source of light in which everything is coming in, there is a net flow of light in, this is also divergent or negative of divergent, convergent. On the other hand, if I take a volume here, nothing accumulates, then divergence is 0. A better way of looking at it would be again in a fluid flow. Suppose there is a point from which, or a fountain, water is going all around. If I make a spherical surface around it, you see there is net flow of water outside. At this point, no matter how small the surface, this point there will be some water going out. So, this point has divergence of V not 0. If I take a sink in which water is going into it from all around, then again divergence is not 0, but it is highly negative. On the other hand, if I see a pipe, although its area may change, the net flow through any small volume is 0. So, divergence at any point is 0. So, I hope this gives you a picture of what divergence is, and divergence immediately you can see is related to source or sink of the field, and stronger the source, which also includes the sink, which is negative source, stronger the source, more the flow, right. Stronger the source, del V dot ds will be larger. Stronger the source implies V dot ds is larger, and this implies divergence of V dV is larger. So, now we are given a mathematical definition to any divergence of any vector field. It is related to the strength of the source, and larger the source, more powerful it is, more the divergence. And it is going to be non-zero only at points where there is a source or a sink, because then there is a net outflow or net inflow. If net outflow or inflow through a small volume is 0, then at that point divergence is going to be 0. So, that is the definition of divergence. With this definition of divergence, there is a related theorem, and that is called divergence theorem. Take any vector field and now take a surface which is of arbitrary shape and encloses a volume. So, this is the volume. In this volume, I divide this volume into very small rectangular boxes. Very, very small. I am making it 2 dimension, but assume these are boxes. And at each point, I apply my calculate the divergence, so that at each point, let us say this point, at this given point, I have divergence of V times this delta volume is equal to summation I V dot ds through each. So, now if I add this over all boxes, I have to add this over all boxes. Look at 2 particular boxes. If I take one box like this and look at an adjacent box, on this common surface, V dot ds for the lower box would have ds going this way, and for the upper box ds is going this way. They are opposite in signs. Therefore, V dot ds will give positive when I do the volume integration here. Suppose it gives positive, it will give negative for the volume integration here. So, the contribution on the surface from this common surface will cancel. Not only these 2 boxes, any 2 adjacent boxes this will happen. So, that the right hand part, when I add over all boxes, contribution from common surfaces will cancel, with the result that the only contributions that will remain will be only from outside surface. Why? Because there is nothing to cancel on the outside surface. So, when I add over all the boxes, I am going to left with integration V dot ds over the surface, over the outside surface, that is the surface of the closed volume, and that is what the divergence theorem is. What it says is that given a volume, large volume, and vector field through this, I did this summation divergence of V delta V over all boxes, and that means entire volume is going to be equal to V dot ds over the outside surface, whereas ds is all pointing perpendicular, pointing away from the surface. Okay. So, this I can write now as integration of divergence over the volume is going to be equal to integration over V dot ds. This is known as divergence theorem. In the next lecture, I will talk about divergence of electric field due to electrostatic charges, and then go on to describe the curl of the electric field. Thank you.